So we should be streaming. Today we'll try to read some stuff about TCP IP stack. I've always been curious about how networking is implemented, um, whereas um, in at university they try to teach you networking from an administrator's perspective, which is not interesting to me because I'm simply not a network admin or a network engineer. I just want to know how it's built, how it's created, so I can, uh, understand it and use it. I can always simply look up Cisco's manuals, for example. So, yeah, let's begin. So this file, I'll make some notes for me. TCP notes. All right. There should be this. There should be this. Let's make it dark reader. All right. Writing your own TCP IP stack may seem like a daunting task. Indeed, TCP has accumulated many specifications over its lifetime of more than 30 years. The core specification, however, is seemingly compact. I guess this is the core specification. Oh, what is that? Toggle metadata. Roadmap for transmission control protocol. There are 60 pages. What's RFC? Internet Engineering Task Force. Request for comments. Whoa. Obsoletes 4000. 2017. I don't know what any of this means. This document contains a roadmap to the request for comments documents relating to the Internet's transmission protocol control protocol TCP. This roadmap provides a brief summary of the documents defining TCP and various TCP extensions that are accumulated in the RFC series. First of all, what the hell is RFC? RFC. Request for comments, and it is a technical document that defines how Internet works. Request for comments. RFCs are created by the Internet Engineering Task Force. This is also important. Internet Engineering Task Force. They are used to establish and maintain Internet standards. So RFC defines how Internet works. Created. RFCs are created. How they are created. Discussion of various parties can be Internet standard, draft standard, proposed standard, and more. For dynamic host configuration, for alright, there are requests for comments. Why is it called request for comments? It's a term used by Internet and other standard setting bodies to refer to the formal documents that outline technical specifications, organizational notes, and standards, particularly for the Internet and networking technologies. How Internet works. Right, IETF, Internet Engineering Task Force. IETF, is it standards organization? Is a premier Internet standards development operation process. About groups. The work of IETF is undertaken and supported by a variety of groups with differing structures, goals, and responsibilities. Open records, license, bring new work to why we need your support. Right, this is some kind of an organization that defines how internet works. IETF and RFCs. IETF is organization and RFCs are the documents themselves. All right. Got back to here. Accumulated many specifications, the important parts being TCP header parsing, state machine, congestion control, and retransmission timeout computation. TCP header, I have, what's TCP headers? I don't know what those are. TCP headers. Different fields of TCP headers, like source destination ports, TCP headers. Transmission control protocol is a reliable transfer protocol. It's the connection sending in data and sends acknowledged by the receiver. In this lesson, we will take a closer look at TCP header and its different fields. It's TCP header parsing. All right. Header parsing. This is a TCP header. This is how it looks. Source, destination, sequence number, acknowledgement number, do, RSV flags, checksum, window, urgent pointer. I have zero idea what this means. I have zero idea. This is a 16-bit field that specifies, all right, each of this stuff means something, right? What's checksum? Checksum to check this header is okay or not. What do you mean? All right. TCP headers. State machine. What's TCP state machine? Let's say state machine. A model that describes different connection can be in from establishing connection to closing it. It's a finite state machine where the TCP implementation at each end of the connection can be in one of several states. All right. TCP uses a three-way handshake. Key states and transitions. The handshake connection. Client sends a SYN packet. In ACK, once the three-way handshake is complete, the connection enters established state. Established must be defined somewhere here. Established. The connection is established and the data transmission can begin. All right. So header parsing, it says TCP state machine. States like closed, listen, yada yada, established, yada yada. Passive close, yada yada. States like this and three-way handshake, SYN, SYN, three-way handshake. SYN. This is the SYN and responds with a SYN ACK. SYN ACK. Closing the connection. Close connection. Means fin ACK. Fin ACK. Right, whatever. Are we having a stream? Yes, we're having a stream. Good. State machine congestion control. What is that? TCP congestion control is a method used by TCP protocol to manage data flow over network and prevent congestion. TCP uses a congestion window and a congestion policy that avoids congestion. Previously, we assumed that only the receiver would dictate the sender's window size. We ignored another entity here, the network. If the network cannot deliver the data as fast as it's created by the sender, it must tell the sender to slow down. In other words, in addition to the receiver, the network is a second entity that determines the size of sender's window. What is a window? Window. TCP congestion window. The congestion window is a crucial mechanism for controlling the amount of data the sender transmits into the network. Network congestion key purpose. Primary goal of congestion window is to prevent network. Alright. Low control congestion control. How much data is sent? Basically, there is a lot of stuff going on here. I'm not gonna go into that. Retransmission timeout computation. And what is this? Congestion control. How much data does one serve? Right, we're back. Retransmission time is a mechanism for ensuring data delivery in the event of packet loss. Packet loss ensure data delivery. If packet loss occurs, dynamically calculated based on timeout. The transmission timeout, round trip time. There's some like round trip time. TO just started when a packet is sent. If no ACK, retransmitted. So within the RTO, retransmission timeout. So packet is sent and timer starts and if no ACK received within the RTO packet retransmitted RTO, which is a RTO, with the RTO being the retransmission timeout. Transmission timeout. All right. So all of this good stuff happens in TCP IP stack 1. The most common layer 2 and layer 3 protocols, Ethernet and IP respectively, pale in comparison to TCP's complexity. In this blog series, we'll implement a minimal user space TCP IP stack for the Linux. The purpose of this posts and resulting software is purely educational to learn networking and system programming at a deeper level. Tune-top devices. What is this? To intercept low-level network traffic from the Linux kernel. So you intercept a network traffic from the Linux kernel. I had no idea you could do that. We'll use a Linux tap device. In short, tune-tap device is often used by networking user space applications to manipulate L3, L2 traffic respectively. A popular example is tunneling, where a packet is wrapped inside the payload of another packet. What? This is a... First of all, we have tune-top device. Then is often used. So this device is often so here's tunneling. Now I have had some experience at tunneling from Hack the Box, but I never understood what tunneling is the idea of carrying lower layer traffic in higher layer or equal layer packets. For example, can be carried in an IPv4 or IPv6 packet. Ethernet can be carried in a UDP or IPv4 or IPv6 and so on. What's your dog? Your dog, Facebook and butts. Fuck this. Certainly various protocols, protocol for tunnels. So the lower layer traffic in higher layer or equal packets. And simple, for example, packet. Tunneling. What is Ethernet? What is UDP? What is IPv4? And what is IPv6? This is all you need to know about this. All right. Tunneling. Packet is wrapped inside a payload of another packet. This, on a high level, makes sense. The advantage of tune-tap devices is that they are easy to set up in a user space program, and they are already being used in a multi-mode of programs such as OpenVPN. As we want to build the networking stack from the layer 2 up, we need a tap device. We instantiate it like this. So a tap device I'm gonna ask stupid. Virtual network interface, a software-based kernel device that allows communication with user-based program and operates a network stack. Whoa, is a virtual network interface? This is too much for me. This is too much. Int alloc taken from kernel documentation networking tab.txt. If we want to build a network stack from the layer 2 up, we need a tab device. We can instantiate it like this: struct ifrag if int fdr. What is this? Open file descriptor 0 this print error clear if flags if tune device tap device if tap or no pi stir copy stir n copy device copy from name device into this could not. After this, the return file descriptor can be used to read and write data into the virtual device's Ethernet buffer. So build data up in the tab device. Instantiate a tab device. Don't tap. After this, the return file descriptor can be used to read and write data into virtual devices. The flag is crucial here, otherwise we end up with unnecessary packet information prepended to the Ethernet frame. You can actually take a look at the kernel source code of the TON device driver and verify this yourself. Ethernet frame. Tune alloc. Ethernet frame format. Payload. Attribute packed. Now, the multitude of different Ethernet networking technologies are backbone of connecting computers in local area networks. Different technologies. LAN. As with all physical technology, Ethernet standard has greatly more from its first version, published in the Digital Corporation until Xerox. First version of Ethernet was slow, and today's standards about per second, and utilized half duplex communication, meaning that you either sent or received data, but not all at the same time. This is why Media MAC protocol had to be incorporated to organize the data flow. Even to this day, carrier sense multiple access with collision detection is required as a MAC method if running an Ethernet interface in half duplex mode. The invention of the Ethernet standard used twisted pair wiring to enable full duplex communication and higher throughput speeds. Additionally, simultaneous increase in popularity of Ethernet switches made largely obsolete. The different Ethernet standards are maintained by working group. All right. Next, we will take a look at Ethernet frame header. It can be declared as C-struct followingly. So this is the Ethernet frame header as C-struct. This is interesting. Frame header as a C-struct. DMAC, SMAC. are pretty self-explanatory fields. They contain MAC addresses of the communication parties, destination and source respectively. Whoa, ether type, what's attribute packed? What is this? Unsigned payload. Unsigned char payload. Attribute pack. No, 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 no. Why does packing happen? Um, why does padding happen? Size of a structure. Why padding? Why struct padding? Padding. No padding. Packing equals no padding. Padding to reduce CPU cycles. I don't really understand why after the type field there is a possibility of several different tags for the Ethernet frame. Alright, overloaded field ether type. What is this? Overloaded field. Is a 2-octet field that depends on its value, either indicates the length or type of the payload, specifically if the field's value is greater or equal to 1536. The field contains the type of the payload. If the value is less than that, it contains the length of the payload. After the type field, there is the possibility of several different tags for Ethernet frame. Oof, my brain is already mush. Field payload contains a pointer to the Ethernet frame payload. Case which will contain ARP or IPv4 packet. The payload length is smaller. Minimum required bytes are appended to the payload requirements. It will also include if other header to provide a mapping between ether types. There, all right. Ethernet frame parsing. A lot of C. This is a lot of C to understand, right? Bufflan, print error, header, handle, frame function just looks at the ether type field of the address protocol, R bucket, format, R bucket. To a protocol address. The key here is that without The minimal implementation of Ethernet frame handling in the ARP is relatively easy and can be done in few lines of code. On the contrary, the reward factor is hence since you get to populate Linux-hosted ARP cache with your own make-believe Ethernet device. In the next post, we'll continue the implementation with ICMP echo and reply. Let's just take a look at that. This wasn't too bad. We could definitely implement this. Tech 2, tags testing the implementation, pin conclusion, and minimal viable network stack that handles Ethernet frames. ARP and IP can be created relatively easy. However, the original specifications have been extended with many new ones, and this post with skimmed over IP features such as options, fragmentation, and the header DCN. It's furthermore is crucial for the future of the internet. It's not a ubiquitous, but being a newer protocol, it's definitely something that should be implemented in our networking stack. All right. Source code for this blog post can be this. In the next post, we want to L4 transport layer and start implementing the notorious transmission TCP. Namely, TCP is a connection-oriented protocol and is reliable within both. All right. Can be found at GitHub. Let's just check out the code. It's 99 people are watching. This is a hacker's perspective. Hacker's user space, TCP IP stack. Level IP is a Linux user space TCP IP stack implemented with TAN-tap devices. Main goal here, learn IP. Fucking learn Linux sockets and API. Data flow and sockets. Samir. Samir, is this from? Yeah, Sami means finish, right? Hacker's browser. You are a hacker, my friend. You don't do this to teach people. Share it for followers. Ping. Alright. This abstract 2. Where's the next? Basic and handshake. We get the handshake. Oh, this is testing the TCP handshake. Installing Arch Linux on Dell. What? Alright, this is the last one. About all right. I will definitely go on